Um, there's really only one more general topic we need to talk about before you have everything you need to. And it's pretty minor. This is going to be a pretty quick video. Um, we know we've worked with actually two different expressions for the force, for the what I'm calling the Lorentz force. You will recall that some people call. I did not throw this away. Okay, now I did. Some people call the Lorentz force this total force. FL equals. I'll go ahead and do this. QE plus QV cross B. I sometimes, just for shorthand, just call the Lorentz force this magnetic portion. I think in textbooks a lot of times you will see this called the Lorentz force, but I don't know. Maybe it's just me, but as long as you understand that the total force due to electric and magnetic fields is this total thing, it doesn't really matter what you call it. I'm not really good at remembering all those names anyway, as I've mentioned to you guys before. Okay, so we've worked with this form. I'm going to ignore the QE for now, and let's just go with here. So we have a QV cross B. So we also have another form for this equation, and that is I dl cross R. And the question is, oh, I'm sorry. Hey. All right, I'm mixing up several equations there. I dl cross B, right? Both of these we say are equal to the magnetic force on moving charges. One of them, we happen to be looking at a charge Q that's moving with velocity V. The other, we have a current I that is through a length L, or dl in this particular case. So the question is, how do these things compare to one another? And the answer is this. If we look at QV, what are we looking at? We're looking at, it's the same as looking at Q per T times V T. Well, so Q per T, what's Q per T? That is, by definition, this is current, charge per unit time. And then we have this other term, VT. I mean, you see what I did here, right? I just divided by T and multiplied by T. But what is VT? Well, the velocity time is just distance. So VT is just, I'll say DL here. We could just as easily write L, right? DL being, if we change this VT to a DT. So we have Q dt, V dt. So, and then we would have dl, but it doesn't matter. Once again, the L is just whatever unit you're going to sum over. If you have a finite number of current, if I had 3 different current lengths here, and they were all a given length L, then I could just do this. I could do the force IL cross B, and I'd be all set, right? If I have and I would just add those up together to get the total force. If I have something like this, then what do? I would change this to a DL and do an integral over this path. So the L and DL doesn't really matter. Okay. So now we know that this is why we can use these two expressions for the force. This one here and the QV cross B. We can use those because they're exactly the same expression. So we are going to extend that now a little bit to the Biot-Savart law. And you will recall that we have something like I dl cross R over R cubed is equal to, and once again, I'm going to go back to this dB notation here. Okay. So you'll recall we have that. Well, what if we don't have something which we can call a current I? What if we just have a charge moving? what if we just have a cube that's zipping along at some velocity v? Sorry, I should not have drawn that as a curved line. You guys know velocity is a straight line that might be moving, changing its angle, but at any instant, it's of course a vector which only points in a single direction. Okay, so what if I have this instead? Well, you can actually go through and do a semi-complicated proof of this, but I'm just going to tell you guys, and by analogy to what we just did, we saw that in our other expression for the force, IdL was equivalent to QV, and in fact, it is. So this is the same as QV cross R over R cubed. So, and I'll go ahead and this point, I'm just going to go ahead and call this B. But what happens if we have more than one cube? We would just add them together, right? So this and this are equivalent forms. That's not quite a rigorous derivation of this, but it's just to let you know that if you see something where you have things stated in terms of current, you can do this. Whereas you have things stated in terms of charge and velocity, you can do this. Okay? I think I'm going to leave it at that. I just wanted to make certain you guys understood that there was an equivalence between these two relationships. All right, that's that.